Hello, in the next 2 or 3 videos, we're going to look at the moment generating function and a few of the properties of the moment generating function. And so to just jump right in, let's let x be a random variable with PDF f. Then the moment generating function of x, denoted by m of t, and probably should put a little subscript there, is defined as m of x of t is equal to the expected value of e to the tx. Okay, and moment generating, we'll understand in a bit why you can generate the moments, like the first moment, the second moment, etc. from this. It should be noted that the moment generating function always exists, but may not be finite, and that is easily seen by it's an integral of non-negative measurable functions. And so you take this times the PDF, which is, the product of measurable functions is measurable, and so it exists, but it may be infinite. And here's the definition of it. So it's the expected value of e to the tx, and if it's discrete, it's the sum over all values of x, and if it's continuous, it's the integral over all values of x, and it's often called a Laplace transform of x. Okay, now our first property is this. It's that if we can find two values, tn and tp, and the tn says that's a negative value, and the TP is, we're going to mean that's a positive value, such that the moment generating function is finite for Tn and finite for Tp. So that is an interval about 0, basically, the Tn and Tp. 0 is contained in that interval. And if we can find this, then every T in this closed interval is also finite. And let's do a proof here. So let's do, for any t0 in this interval, we can find a theta that's between 0 and 1, such that a linear combination of these endpoints is the t0. Okay. Now, one note before we go on is that Tn can be represented as a negative number, Tp is a positive number, and some T0 between them. Now that we can develop a linear combination of those, and that's what I just said earlier, is that that this value T0 is a linear combination of those. Okay, so now e to the x is convex. Okay, so in the following proof, it's either going to be positive, x is going to be like this, or it's actually the exponent will be negative, then it's concave this way. But in either case, if we take the endpoints and go up to the exponential function, and then we find a linear combination of those endpoints, that point is always going to be bigger than that point. And that's because that this is a convex function. That's pretty much the definition of it. So the e to the t0 is that lower point. And we said t0 is a linear combination of the endpoints. But then we also said a linear combination of these points, which is e to the tn and e to the tp, and that's if we use the same theta, then they're right above each other, and this is always bigger than that. And so I could have a more rigorous proof, but I think intuition also goes quite a long ways, and this is the intuition of what we're going to use in a second. So the expected value of t0, which is this, is less than or equal to the expected value of this. But though this is a constant, so it comes out front. This is a constant, so it comes out front. But each of these values are finite. And then times a finite number, they're finite. So this is finite. So every t0, the moment generating function, which is this, is also finite. Now let's look at another piece that we need to have, that if the kth moment is finite, then every moment below k is finite. Okay? And I proved this in a video I put out, derivatives of a characteristic function are bounded. So you'll find that proof. It's very simple and short. So now let's look at this bullet point. That if we have two numbers, Tn and Tp, remember N stands for negative and P stands for positive, such that the moment generating function is finite at those points, then all moments exist and are finite. Okay, well, that's one step farther than we did in the last moment, but here is the proof. So let's let t be the minimum of these values, and so it's a positive number. So what we're doing is get an even interval about 0, and then we know that mt is finite because of the two bullets ago, that every value in here is finite, because if Tn is finite and Tp is finite, then every value, then T0 has to be finite. So now, if we look at the Taylor expansion of these two values, e to the minus T0x and e to the T0x. So this first one, this is the Taylor expansion, and then the second is, here's the Taylor expansion, and then if we add these, we get 2, but then this term drops out, and then we get 2 of these, and the next term drops out. So every other term drops out, which is this. We're adding the positive, or the rate, the even exponents. So this can be thought of as something to the 0. So that's why it's 1. But note, every term here is positive. Okay? So if we just pluck out one of these, and it doesn't matter which ones, for some, let's call it k. So let's let n equal k, and this is one of those terms. We're ignoring all the other positive terms. This has to be less than this over here. So then if we take the expected value of this side, take out the constants, what we do, so that's the expected value, it's less than or equal to the expected value of these. But these are the, we've established earlier that these are finite. So that says that this moment is finite. And this is for any k to infinity. And if these higher moments are finite, then every moment below it is finite. So if we can find an open interval about 0 that, that the endpoints are finite, then every moment exists and is finite. So then we've shown that this is finite, which implies that for all m less than 2k is also finite. Okay? This for every k, so it exists, and we're done. So there's only one other point, that the contrapositive to this is also true. Since this is true, the contrapositive is true. And it says if any moments are infinite or do not exist, then the moment generating function is not finite in any open interval about 0. And that's the contrapositive of the previous statement. And so the classic example here is, a Cauchy distribution where the mean does not exist and the second moment is infinite. So there's no interval which around 0 that the moment generating function is finite. Okay, but one point that it doesn't point out is that if we can't find an open interval about 0 that has finite endpoints, it doesn't tell us anything about the the moments of that distribution. And a classic example is a log normal. You can't find an open interval where the moment generating function is finite, but every moment of a log normal is finite. And so you have to be careful with these two properties. Well, anyway, that's all I have for today. There's going to be one, maybe two more videos on the characteristic function. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.